A neutron star is already the densest confirmed object in the universe, matter crushed so violently that a single teaspoon would weigh 1 billion tons. But theory says there's a point where even that isn't the end. Push the density further still, and neutrons themselves may not survive. They could break apart entirely, dissolving into something stranger than anything confirmed to exist anywhere in the cosmos. To understand what that means, you first need to understand what a neutron star actually is. Ordinary matter is mostly empty space, atoms held apart by electromagnetic forces. Crush a dying star hard enough, and that space collapses, protons and electrons merging together into neutrons, packed edge to edge with nothing left between them. That's a neutron star. But some physicists believe there's a further step. If the pressure inside a neutron star's core climbs high enough, the neutrons themselves may break apart, releasing their fundamental building blocks, particles called quarks, which normally never appear on their own. Under extreme enough pressure, those freed quarks wouldn't stay as simple up and down quarks either. A portion of them would transform into a rarer, heavier variety called strange quarks, producing an exotic mixture physicists call strange quark-matter. A star made almost entirely of this material is called a quark star, or strange star. Here's the part that genuinely unsettles physicists. In 1984, physicist Edward Witten proposed something called the strange matter hypothesis, and it isn't a small claim. He suggested that this exotic mixture of up, down, and strange quarks might actually be more stable than ordinary atomic nuclei, the very particles that make up you, this planet, and every star in the sky. If that's true, strange quark matter wouldn't just be an unusual form of matter found in extreme stars. It could represent the true lowest energy ground state of matter itself, with ordinary protons and neutrons simply existing in what's technically a falsely stable state. One that has simply never encountered the right conditions to convert. To put the scale of these objects into perspective, the smallest, most tightly compressed neutron star theoretically possible measures roughly 17 kilometers across. A quark star, under the same conditions, could measure under 11 kilometers, smaller in diameter than the Grand Canyon is wide, while containing more mass than our entire sun. Held together not by the ordinary pressure that supports a neutron star, but by the strong nuclear force itself, one of the fundamental forces of nature, acting directly across the whole star. Here's where this stops being pure theory. Quark stars have never been confirmed to exist, not with total certainty, but the observational evidence has been building steadily. One object in particular, called Hess J1731347, has puzzled astronomers for years because it appears significantly lighter and smaller than physics says a neutron star of its type should be. Exactly the signature theorists expect from a quark star instead. In December 2025, a fresh analysis of a separate pulsar, PSR J06143329, using precise measurements from NASA's NICER mission, found substantial statistical evidence favoring a strange quark star interpretation over every standard neutron star model tested against the data. And in February 2025, a team at Guangxi University proposed something even more remarkable, that they may have directly witnessed one of these stars being born. Analyzing a gamma-ray burst called GRB 240529A, the team found a sequence of energy signatures matching almost exactly what decades-old theoretical models predicted the birth of a strange star should look like. Distinct emission episodes and X-ray plateaus lining up with 1980s-era predictions in a way that's difficult to dismiss as coincidence. Now, to be properly honest about where this stands, none of this confirms quark stars exist beyond doubt. Every candidate remains just that, a candidate, consistent with the theory but not yet proven beyond alternative explanations. What has changed is the sheer number of independent lines of evidence, from unusually light neutron stars to precise radius measurements to a possible direct birth event, all converging on the same conclusion within the last 2 years alone. And there's one more thread worth sitting with. If Witten's hypothesis is correct, and strange quark matter really is more stable than ordinary matter, then contact between a quark star and an ordinary neutron star could, in theory, trigger a chain reaction. converting the neutron star's matter into strange matter entirely. It's a genuinely speculative idea discussed carefully in the scientific literature rather than treated as any kind of imminent concern, but it's a striking reminder of how strange the implications become once you take the underlying physics seriously. What do you think? If strange matter really is more stable than the atoms that make up everything around us, does that change how you think about what ordinary matter even means? Let me know in the comments. Subscribe because next time we are covering OJ287, a pair of supermassive black holes locked in orbit around each other, one repeatedly punching straight through the other's disk of gas on a schedule so precise, astronomers can predict it down to the week.